So guys, welcome to our channel once again. In today's video on our WAEC Physics Exam Revision Series, we have here these 10 WAEC repeated questions to answer on the topic Hooke's Law, Young Modulus, and work done in springs and string. So guys, in short to stay till the end of this video, let's go ahead and start with the first question here. It says, the ratio of tensile stress to tensile strain is known as A. Modulus of rigidity, B. Modulus of elasticity, C. Shear modulus, D. Young modulus. So guys, the answer to this question is option D. Young modulus. Let's go ahead and consider the next question, guys. So guys, the next question here is question number 2. It says, which of the following statements about a spring balance and or a chemical balance is not correct? We have A. The chemical balance operates on the principle of moments. B. Either may be used to measure the weight of a substance. C. The reading of a spring changes over the surface of the earth, while that of the chemical balance remains constant. D. The spring balance operates on Hooke's law. So guys, the answer to this question here is option B. And if you check out, all the options here are correct aside option B. So that's it for this question. So let's go ahead and consider the next question, guys. That's question number 3 here. It says, the potential energy in an elastic string of force constant K, which has been extended by x meters, is expressed as A. Kx squared, B. half kx, C. half kx squared, D. kx. So guys, the answer to this question is option C. half kx squared. So let's go ahead and consider the next question, guys. The next question we have here is question number 4. It says, an elastic string of force constant 200 Newton per meter is stretched through 0.8 meters within its elastic limit. Calculate the energy stored in the string. So guys, here the energy stored in the string can be calculated as half kx squared. So we have 200 times 0.8 squared all over 2. So guys, that will give us 64, and that's it for this question. Let's go ahead and consider the next question, guys. So guys, the next question we have here is question number 5. It says, materials that can be stretched and still return to their original form when the stress are removed are said to be. Of course, obviously the answer to this question is option A, guys. So that's elastic. So let's go ahead and consider the next question, guys. So the next question we have here is question number 6. It says, the energy stored in a spring of stiffness constant K is 2000 Newton per meter when extended 4 cm is. So guys, in order for us to calculate this, we are still going to use half Ke squared. So in this situation, we are going to have 2000 times 0.04 squared. So this is cm, converting it to meters, that's 0.04 squared, and then this over 2. So when we do that, we're going to have 1.6 joules, and that's option B here. So let's go ahead and consider the next question, guys. So guys, here, question number 7 here says, a body of mass 11 kg is suspended from a ceiling by an aluminum wire of 2 meters and diameter 2 mm. Calculate the elastic energy stored in the wire. So the Young modulus of aluminium is 7.0 times 10 to the power of 10 Newton per meter squared, and then G is given as 10 meter per second squared, and then pi is given as 3.14. So guys, let's note that the Young modulus A is equal to FL over AE. So guys, since we have the Young modulus given here, we can calculate for the force by multiplying the mass with the acceleration due to gravity here. Then we can also calculate for the area as pi r squared. So let's find E here. So we are going to find E in order for us to be able to solve for the energy. So let's find E here. So E is going to be FL over EA. So the F, which is the force here, is 110 newtons, which is 11 times 10 meter per second squared here. So that's 110. Then times the length, which is 2 meters. So 110 times 2, and this will be all over the E, which is the Young modulus here, which is 7.0 times 10 to the power of 10, and then times the area, which is the pi r squared. So pi is given as 3.14, then times r squared. So we have the diameter. So the diameter over 2 is the radius. Actually, the diameter is 2 mm, which is 0.002 meters. So we'll divide that by 2, which is 0.001, and then we'll square it. So when we square it, we'll have 10 to the power of negative 6. So that's it. So the area is 10 to the power of negative 6 here. So when we input all these and calculate, we are going to have 10 to the power of negative 3. So in that case, since the elastic energy stored in the wire can be calculated as half Fe, we're going to have half Fe to be the force here, which is 11 kg times 10 meter per second squared. That's 110 newtons. So the force here, 110 times the E, 10 to the power of negative 3, then over 2. So that will give us 5.5 times 10 to the power of negative 2, and that's option D here. So let's go ahead and consider the next question, guys. So we have a diagram here in this next question, question number 8. It says, the diagram above represents the graph of stress against strain for an elastic wire. The point Q on the graph is the A, elastic limit, B, yield point, C, proportional limit, D, breaking point. So guys, the answer to this question is option D, that's the breaking point. So let's go ahead and consider the next question, guys. So the next question here says, a spiral spring of natural length 30 cm and forces constant of 20 Newton per meter is compressed to 20 cm. Calculate the energy stored in the spring. So guys, we're going to use half kc squared here for this, and then we are going to have that C is the natural length minus the compressed length, that's the 30 minus 20, and that's 10 cm. But guys, we have to put this in meter. So 10 cm over 100 is going to be 0.1 meter. So guys, if we have this as half kc squared, then k is 20, then times c squared is 0.1 squared. So 20 times 0.1 squared over 2 is going to give us 0.1, and that's option A here. So let's go ahead and consider the next and last question, guys. So that's question number 10 here. It says, use the following data to determine the length of a wire when a force of 30 Newton is applied, assuming Hooke's law is obeyed. So we have the data here, and let's go ahead and sort this out together. So let's recall that F is equal to KE. So if F is equal to KE, then K is equal to F over E. So let's note that here, when there was no force applied, that's when F was 0, the length of the wire was 500 millimeters. So When a force of 5 Newton was then applied, the length changed to 500.5, meaning that the extension here is 500.5 minus 500, and that's 0.5. So we can simply get K by dividing 5 by 0.5, and that will give us 5 over 0.5 is 10. So K is now 10. So if we have K to be 10, we can now easily get the length of the wire when the force of 30 Newton was applied. We'll still do that F is equal to KE. So in this respect, we are going to find E, which is the extension, and then we'll now find the length by subtracting 500. So in this case, we have E to be ELF over K. So the ELF is 30 and K is 10. So 30 over 10 is 3. So in that case, the new length of this wire will be 500 plus 3, and that will be 503. So option A is the answer to this question, 503 millimeters. So guys, this is where we'll end this video for today. If you enjoyed this lesson, please give it a thumbs up. Don't forget to subscribe to this channel if you're not yet a subscriber. Also, if you have any specific question regarding this video, you can drop your question on the comment section below and we'll ensure to give you a response. So finally guys, you can join our YouTube channel community where we post major updates on WAEC examination. So to join this channel community, hit the join button below and we'll see you right there. Thank you once again for watching this video.